Imagine this. You are hiking deep in the mountains. No signal, no towers in sight. Yet your phone suddenly receives a text straight from space. This isn't science fiction. It's Starlink's new direct to cell service. And for the first time, researchers have analyzed how this technology really performs. This is Starlink's direct to cell explained. In June 2025, researchers published the very first crowdsourced measurement study of Starlink's direct to cell network, covering real world data across the United States. The study reveals where the system works, how well it performs, and what the future may hold. It's the first time that a large scale scientific investigation has looked directly at how ordinary smartphones connect to satellites in orbit. To understand the significance of this, we need a bit of context. Traditional geostationary satellites orbit far above the Earth at around 36,000 kilometers. They cover huge areas, but with one major drawback: high latency. That makes them less than ideal for real time communication. Low Earth orbit satellites, often called as LEOs, are different. They orbit just a few hundred kilometers above us. Because of that, they deliver much lower latency, and with enough satellites in orbit, they can cover the entire planet. Starlink is by far the largest LEO constellation today, and with direct to cell or DS2D, they are taking an ambitious step forward. The idea is simple: let ordinary smartphones connect directly to satellites without the need for any special antennas or ground terminals. Right now, the service is limited to text messages using T-Mobile's licensed spectrum in the United States. But it represents a fundamental shift because for the first time, the same device we carry every day can tap directly into a satellite network. So, how did researchers study this? They collected millions of measurements from Android phones between October 2024 and April 2025. Each measurement captured details like signal strength, signal quality, interference levels, and the exact GPS location of the device. By comparing these to ordinary T-Mobile terrestrial data, the researchers could see where direct to cell connections occurred and how they performed in the real world. They didn't stop there. They also factored in satellite launch timelines, T-Mobile coverage maps, and county population data. The goal was to paint a complete picture of how people were actually relying on Starlink's direct to cell service across the country. To estimate performance, the team applied a modified version of Shannon's formula, which links signal quality to the theoretical maximum data throughput. This allowed them to go beyond signal bars and predict the real capacity of each satellite beam. So, what did the study actually find? First, they noticed a clear link between the rollouts of Starlink's second generation satellites and the growth of direct to cell connectivity. As new satellites went online, more cell identifiers appeared in the data. In other words, the crowdsourced measurements were able to track satellite deployment in the real time. Second, the service showed up exactly where you would expect, in places with poor or no traditional coverage, remote counties, national parks, areas with sparse population. But it wasn't just rural America. During emergencies like hurricanes in Florida and wildfires in Southern California, direct to cell suddenly became active in areas where terrestrial networks were damaged or overloaded. That suggests Starlink may become a critical backup during disasters. Some counties stood up with very high usage. In places like Knott County, Kentucky, or Florence County, Wisconsin, direct to cell accounted for more than 85% of mobile connectivity in the collected data. Often, these were regions near large national parks or mountainous terrain where traditional cell towers simply don't reach. What about actual network quality? On average, the received signal strength from satellites was lower than what you would get at the edge of a normal cell tower. That's not surprising, given the distance and lower transmission power, but interestingly, the signal quality was often better. Why? Because direct to cell is still SMS only. With very few active users, that means very little network congestion. Signal to interference and noise ratio, or SINR, was generally lower than terrestrial networks, but again, the low demand meant the system was stable. Researchers also observed a stronger correlation between signal strength and quality in direct to cell compared to traditional mobile networks. That's because satellite links have more predictable geometry. There's less random variation compared to signals bouncing through buildings and towers on the ground. In short, weaker signals but cleaner and more consistent links. Of course, the big question is how fast is it? By analyzing the measurements, the team estimated that the mean capacity per satellite beam is currently about 4 megabits per second. That's not enough for streaming or heavy internet use, but it's more than enough for emergency communications and basic connectivity. And here's the interesting part. In March 2025, regulators allowed Starlink to increase its out of band emission limits. This effectively lets the satellite transmit at higher power. With that change, throughput could rise to around 12 megabits per second per beam. Looking ahead, future upgrades could expand the capacity even further, either by using wider bandwidths or by deploying more satellites to densify the constellation. But spectrum access remains a big challenge. Without regulatory approvals to use more frequencies, growth will be limited. So while the technology is ready, policy may end up determining just how fast direct to cell can expand. So what does all this mean? First, Starlink's direct to cell is already viable. It's not replacing terrestrial mobile networks, but in remote areas, it provides a real coverage where nothing else does. Second, in emergencies, it can act as a safety net. The data clearly shows that when terrestrial networks go down, satellite connections step in. Third, it opens up new ways of thinking about mobile planning. Instead of every carrier trying to build towers in hard to reach places, satellite coverage could fill those gaps. And finally, it raises important policy questions. Who controls the spectrum? How should satellites share frequencies with terrestrial operators? And what happens when multiple satellite companies start competing in the same bands? Starlink's direct to cell service is still young, but it's already reshaping the idea of mobile connectivity. From life-saving emergency coverage to bridging the rural digital divide, it may soon bring us closer to a world where being out of signal is truly a thing of past. The technology is here, the satellites are already overhead, and as capacity grows, we may soon take for granted something that once seemed impossible, a direct connection from our phones to space.